So why do we look at them? Okay. So it's because polarity plays a major role in the strength of what are called intermolecular forces. And affectionately abbreviated IMF. Think of IMFs well, they're kind of like stickiness. Now, if you want to lose some points, tell me that intermolecular forces are bonds. They are not bonds. Bonds are much, much stronger, and they are directly between, for the case of covalent compounds, which is what we're dealing with here, they are pairs of electrons directly between two atoms. That's a bond. Intermolecular forces are not so much direct interactions between atoms, though we could argue HB interactions are close to that. Instead, it is regions of high electron density attracting regions of low electron density. So the idea that opposites attract. Okay, so IMFs, not bonds. So we've got London dispersion forces are the weakest. These London dispersion forces, it's the baseline. Because both polar and non-polar substances have these L, D, Fs. So that's the baseline. London dispersion forces are tiny, temporary, induced dipoles caused by a momentary asymmetric distribution of electron density. All right, so everybody has them. For nonpolar compounds, London dispersion forces is it. Let's try, let me try to draw a nice even distribution of electron density. So I'm going to try. Okay, that's not horrible. Okay, so an even distribution of that electron density. Okay, again, go back to that idea of symmetry. So it's nice and symmetric. What happens is that something else comes along and disturbs this even distribution. That's why it's called an induced dipole. What happens is instead of, so here we have some sort of disturbance. Instead of having this nice kind of symmetric, what happens is the part here will shrink and becomes more of a gourd shape. So when we have the disturbance, we have an end that's a little negative. I'm sorry, that's how it would be a little positive. A little positive. And then the other side is a little negative. The electron density can shift back to being symmetric. So because it has this ability to shift one way or another, we can end up with it having that asymmetry, that tiny, tiny little dipole, dipole. That little separation of charge, that's what leads to attraction between the two molecules. Individually, London dispersion forces are the weakest. But that does not mean if you have a lot of London dispersion forces that overall it can't exhibit really, really strong interactions between molecules. Gasoline is nonpolar. So gasoline molecules interact with other gasoline molecules through these London dispersion forces. Oil is also nonpolar. So it also only can interact through these London dispersion forces. Motor oil, though, you know, oil is more viscous. It doesn't evaporate as fast, if at all. It's got a higher surface tension, just all kinds of pieces. And all of those pieces are related back to the strength of the intermolecular forces. So even though gasoline and oil both are nonpolar, both just have LDFs, the total amount of LDF, these London dispersion forces present with molecules of oil, are stronger than what we find with gasoline. And it's because the molecules themselves in gasoline are much shorter compared to an oil. And so if you have two small pieces that are sticky together, or two long pieces that are sticky, well, the longer pieces that are sticky, it's going to be harder to get them to come apart from one another. The London dispersion forces, those require a little bit more explanation than the other ones, I think. So dipole interactions. And essentially, the whole idea here is that opposites attract. And so dipole interactions form between molecules of polar compounds. And that is the first key difference. Dipole-dipole interactions, you must have polar compounds. So what happens is the partial negative part portion of one molecule is attracted to the partial positive portion of a second molecule. So with dipole-dipole interactions, we're not relying upon this shift of electron density, which is admittedly going to be really small. We are actually dealing with things that have a positive end and a negative end. Because of that, we have a larger separation of charge. That larger separation of charge means that the attractions are going to be stronger. So essentially that separation of charge, it can act almost like a stronger magnet would be one way to think about that. And so because you have stronger magnets, you have stronger attractions between those two magnets. Those are my dipole-dipole interactions. So we've got London dispersion forces, we've got dipole-dipole interactions, and then the third one are called HB interactions. Now, your book and your lab gives them their full name. And their full name is hydrogen bonding interactions. And I prefer HB interactions. The reason why is it hopefully emphasizes the fact that when you break interactions between separate molecules, you are not truly breaking chemical bonds. The molecules themselves stay together. So when we have water boiling or water evaporating, the interactions between the water molecules break. The water molecules themselves stay intact. It's still an oxygen bonded to two hydrogens. Hydrogen bonding interactions, or these HB interactions, it's a special case of dipole-dipole. So if you see, if you pick out that something has the capability of forming hydrogen bonding interactions, these HB interactions, you know automatically then, hey, it's polar. So on top, you know, in addition to HB, you have dipole-dipole. And then of course, you automatically have those London dispersion forces. So these hydrogen bonding interactions are just another layer of stickiness. All right, so here's what you have. A hydrogen atom covalently bonded to a small, highly electronegative element. And we have 3. We've got fluorine, oxygen, or nitrogen. So that hydrogen connected to F, O, or N will interact strongly with a pair of electrons on fluorine, oxygen, or nitrogen. Of a second molecule. What we have to have is we have to have on molecule 1. I don't care what the rest of it is. I'm just going to emphasize this part. OH. And then I'm going to have O. H. And this is molecule number 2. The interaction that is occurring is between the lone pair on molecule 2's oxygen and the hydrogen that is on molecule 1's oxygen. So here is my HB. And sometimes rather than draw it just as a line, we'll have a tendency to draw dots. And let me do that because it just makes me feel. Whoop. So there's your HB interaction. All right, so if you have a nonpolar compound, you get London dispersion forces. If you're a polar compound, on top of the London dispersion forces, you have dipole, dipole. If you have polar with either HO, HF, or HN on top of your London dispersion forces, on top of the dipole-dipole interactions. And I'll just abbreviate those dip-dip. You have hydrogen bonding interactions. So you get all three flavors. All other things being equal, these ones should exhibit strongest IMF. Okay. So what intermolecular forces are present between molecules of ... If I've got something like CH3, CH2, CH, come here, 2, OH. This certainly looks a lot worse than any of the Lewis structures we've done so far, which maybe makes you think, oh my God, I can't do this. Yes, you can. And as I mentioned in lecture Wednesday, these are in many ways a lot easier to handle in terms of Lewis structures. This is what's called a semi-structure or semi-structural formula. It gives you hints as to how this molecule is put together. And this is a class that's called an organic molecule. And these structural formulas are written all the time. If I start off, hydrogen cannot be in the middle. If I look at, I have a carbon, a carbon, a carbon, and an oxygen. Carbon has 4 valence electrons. 1, 2, 3, 4. Carbon has 1, 2, 3, 4. 2, 3, 4. Oxygen, 1, 2, 3, 4, 5, 6. Carbon is in the middle. Just no ifs, ands, or buts about it. You got a carbon, it's going in the middle. So if these carbons are connected to each other, this terminal carbon has the spot to make 3 more bonds. What do you think? There's a reason why this end has a CH3. There's my CH3. What's the next piece? Well, it's a CH2. I'm pretty sure I can only put 2 hydrogens here. What comes next? Another CH2. And then I have H and O. Carbon can only make 1 more bond. Hydrogen's never, and I've got a hydrogen and an oxygen left to hook into this molecule. Hydrogen can't be a middle, can't be a center, so it's got to be the oxygen. The reason why I say these are sometimes easier to draw than some of the Lewis structures we were doing in class is because the structure tells you, okay, that the formula gives you a real big indication as to how this thing gets put together. All right, now, what intermolecular forces are present? I'm always going to start off with London dispersion because everybody gets them. Then I wholeheartedly admit I look for something that isn't carbon. So first thing I do is give everybody LDFs. Now I'm going to look for something that's not carbon or hydrogen. So in this case, I have the oxygen. So I go to look for something different. There's an oxygen. Is there a hydrogen connected to that oxygen? Yes. Because the answer here is yes, that means I have HB interactions. If you have HB interactions, you automatically get dipole, dipole. So the first one, I give everybody London dispersion. Then I start looking for something that is not carbon or hydrogen. I have oxygen. At this point in time, I could just say, this means it's polar. Well, if it's polar, that gives me dip-dip. And then, is there hydrogen connected to the oxygen? Yeah. So I get HB interactions. So I have 2 and 3. One more quickie example, and that's acetone. So CH3, CO, CH3. One of the hints that the lab report, the lab gives you, is it tells you what the skeleton is. So it tells you your skeleton for acetone is C connected to C, connected to C, connected to O. That's not to say it fills up octets. It most certainly does not. But it at least tells you what atoms are center atoms, or could be center atoms. For sure, carbon. And so I'm going to do the exact same thing that I did before. Carbon 1, 2, 3, 4. Carbon 1, 2, 3, 4. Carbon 1, 2, 3, 4. Oxygen 1, 2, 3, 4, 5, 6. And now toss in those, what do we got? Hydrogens, right? And so we have H, 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 boom, 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 H, H, and H. Well, now what? This looks an awful lot like the example that we did in class, where instead of carbons here and here, I had just hydrogens. So if you recall, what I had you do with that one is this oxygen is 1 electron shy, and the carbon is 1 electron shy. So we're going to bring those 2 electrons in and make a new bond. So our picture becomes C, 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 double bond O, boom, 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 H, 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 H. Now again, what intermolecular forces? Right off the bat, I know LDF. Is the molecule polar? Does it have a polar bond? carbon, hydrogen bonds, non-polar. You can look up the numbers. It's fine. It's just flat out, I'll tell you right now, the difference in electronegativities, carbon, hydrogen, is 0.4. So we consider it to be essentially non-polar. That means that in order to be polar, this interaction between carbon and oxygen better be polar. Well, carbon electronegativity is 2.5, and the electronegativity of oxygen is 3.5. Polar bond. That means that on top of LDF, I have dipole, dipole. Again, if you want to call it dip-dip, I'm good with that. So is there a hydrogen bonded directly to O, N, or F? Well, for this, I'm just looking here. I don't have any hydrogens directly connected. Nope. So that means no HB present. And that's all she wrote. Okay. I'm going to leave off there, and when we come back together after break, I will actually start talking about gases, and then we'll get into talking about some solutions. This means that you're on your own for working yourself through some of the impacts of intermolecular forces. Now, lab is set up to give you some hands-on experience with it. And the text has some good information as well. But I'm going to go ahead and leave you with those pieces to work through yourself. And like I said, when we come back together, we will, we'll start on gases and go from there. So I hope you all have a great break. I will send out an email /schedule for room assignments for lectures on Wednesday. it looks as though we're still doing our split lectures. So if you are section 101, cadre 1, you still come and see me at 8 a.m. If you're cadre 2, you still come see me at 9:30 a.m. And if you're in the afternoon, we will still split the 2 to 3:30 or 3:20, and then the 3:30 to 4:50. So